Next keynote speaker is Professor David Ann, and he's a Chief Technologist, National Center for NetShape and Additive Manufacturing Technology Center, Coventry, UK. The topic he would be covering is impact of additive manufacturing on the high-value manufacturing sector. Can we have a round of applause for Professor David?
Professor David Ann Wimpenny is one of the best scientists in the world in additive manufacturing and co-founder of Global Additive Manufacturing Association called GARPA, and we are very happy to have him with us, and we are very proud to be having with us with him. So great welcome, sir.
Good afternoon. I've chosen the shortest presentation I have available with me, so I hope I won't keep you too long. So a few moments words before we get started. The title of the presentation was to do with the impact of additive manufacturing on the high-value manufacturing sector. That's quite important to bear in mind. We're not going to be using this technology for making very cheap and cheerful parts. These are going to be used, at least in the short term, for expensive parts. First of all, I'd like to thank the organising committee, particularly George Kumar, for inviting me to the event today, and also the Science Innovation Network, who helped support my trip to India. A long overdue trip to India, I have to say. So I work at the Manufacturing Technology Centre. It was founded in 2010. It's an independent research technology organisation. And it opened its doors on the 1st of August 2011, so it's quite a new organisation. The reason I'm showing these slides is that one of the things that every country has to work out is how does it get involved in additive manufacturing. And we've seen this morning discussions about how does India approach its position in additive manufacturing. I'm going to give you some slides that may be a consideration for how India does it going forwards. There are plenty of different models. It's not the only way of doing it. You'll notice that this organisation, the MTC, was founded by 4 leading research organisations, 3 universities, so Birmingham University, Loughborough and Nottingham University, and the Welding Institution. We also have lots of support from industry, particularly the aerospace sector. I think this morning there was a discussion about the value of death, and one thing we can say is that universities are very good at this stuff. Particularly the UK. The UK has some of the leading universities in the world and has generated more Nobel Prize winners than any other country. Much not enough of this going to the companies, not enough of commercialisation. Much of the technology that's developed in the UK ends up being developed elsewhere in the world. So the UK government realises the problem and said we need to try and bridge this valley of death. And our measure is not the number of publications we produce or the number of students we teach. We are measured entirely about the number of technologies that get through to being commercialised. And that alters the behaviour of the organisation. Just a bit of vital statistics. We've been going since just over 3 years now. We have 350 staff. We have 75 industrial members. Some of those guys you're probably familiar with, people like Rolls-Royce, Sandvik, who are here today, Alstom, GKN, and also some smaller organisations who are very important. The small organisations that make the equipment, that without those guys we couldn't actually do the research. We have lots of different technologies within the Manufacturing Technology Centre, and one thing I would say is that we'll talk a little bit later about the NetShape additive manufacturing theme which I set up. But it's important that we've got quite a wide spread. This is a sort of ecosystem that supports itself. If I need parts to be measured, I can go to the NDT metrology group. If I need something to be simulated, I've got the guys there already to help me. Another important thing that we do is we do training now. And I think this morning the discussion is about skills. This is really important for the industry. We're having to pay machine operators, good machine operators, over £60,000 a year because we can't get people to run the machines. So unless we start to skill them up, we won't be able to run the business. The actual growth of the sector in the UK will be dictated by the amount of people we have available. Okay? So it will kill the industry. So we've set up the Advanced Manufacturing Training Centre with £36 million of government funding, £1 million worth of funding from Lloyds Bank, and we're training the next generation of apprentices and graduates. Okay, this is really important. Skills are probably the single biggest concern we have in the UK's manufacturing sector. Well, over the last 30 years, and it's about 30 years now, there's been well over 30 commercial AM systems have been developed. Not all have been successful. There should be a memorial somewhere, perhaps in America, to all the machines that came and went. You know, solid ground curing. Can anyone remember solid ground curing? Okay. Laminated object manufacturing.
Yeah, it's obsolete now.
Yeah, all obsolete, yes. But that's fine, that's how things are. One thing I can tell you, and I don't want to spoil the guys who are selling machines, I don't think the best technology has been invented yet. So if you guys want to make yourself a fortune, start thinking, okay? Because the technology we need for production is different than we're using for prototyping. I'll talk a little bit about the materials. With lots of technology being developed, we now have machines for making polymers, parts, and metal parts and ceramic parts. I will focus on metal technology because that's really where the current pull is from industry. However, I have to say, we're now seeing demand coming through from serious industrial players for ceramics, for polymers, okay? They will come along, so please don't get completely focused only on metals. These are the metals technologies, and we have presentations this week from the guys from X1. This is technology which will really offer production volumes that we can't achieve with these other technologies. So what's the impact on the high-value manufacturing sector? Well, these are the key manufacturing sectors, and actually the real users at the moment of additive manufacturing for end-use parts are the medical and dental sector. They're important, and that will probably dominate the next 10 years of development. And this is the reason why you get people like Steve Rangers, from head of GE's Aviation Research Development Group, saying you are able to produce designs and components which you could never do with traditional manufacturing. If you're making the part as it currently is designed for a traditional technique, you are missing the point. There is no point in using additive manufacturing. However, why are people moving from well-developed techniques? I have to say that additive is not the only game in town. We used to have something called machining, and casting, and forging. These techniques haven't disappeared. They're still very good techniques. The reason the aerospace sector has been driven to additive manufacturing is we've got massive growth in production volumes, unprecedented in the aerospace sector. $2.73 trillion of orders. Okay. We need improved performance. I mean, all these people flying, we can't kill the planet. So we have to find ways, more efficient ways, of making aero engines. And it's also about cost. We all want to pay less and less for our tickets to fly. So the growth in production volumes, and I think we mentioned, already a couple of people mentioned about how much waste we generate when we machine. Well, we have parts that have a buy-to-fly ratio of 20:1, which means that for 20 kilos of billet, we have 1 kilo of part. We end up throwing away over 90% of the original material. That material, if it's titanium, is expensive, and it can't be easily recycled. The situation is getting worse as we get thinner and thinner walled parts. And recently, with a study done by Airbus, they found out that 60% of the cost of manufacturing a component lies in material. Right? That's crazy. You know, that's in some cases, that's more than the target price for the part. with additive manufacturing, we can get ratios, buy-to-fly ratios, approaching 1-to-1. Another issue is about improved performance. Who flew here today, for this conference? Who's still awake? Okay. Most of you flew, probably, I would guess, unless you're living locally. I mean, over the last 50 years, the efficiency of aero engines has improved dramatically. We've got fuel efficiency of 70%. We've got aircraft which are 75% quieter, carbon monoxide by 50%, unburnt hydrocarbons and smoke by 90%. If that was the car industry, we'd be doing cartwheels in the street. Okay. However, to get any further improvement, we have to use additive manufacturing. We've tried everything else. We've tried composites, we've tried other materials and processes. Additive is the last hope. And you've seen this example will be used on numerous occasions over the next couple of days. The GE LEAP engine. I think it's actually not the best example in terms of what it does in terms of weight reduction. The weight reduction is relatively small, 3.25%. What it does do is it assembles a large number of parts which they were having difficulty with into one single part. So they've improved the reliability of the end product. The thing that really drives it is the volumes. It's 100,000 parts. That is, in additive manufacturing terms, that represents the last 10 years of production, probably. It's a leap forwards for the industry. Once you go into production, you go from having an industry which makes ones and twos to making thousands. We're not on our own here. We've got competition from all around the globe. We have this example. This is an aerostructures part produced in China, which is intended to fly next year, produced by laser cladding, laser melt deposition, in machines that can produce parts up to 5 meters tall. But there are some barriers to introduction. It's not all good news. The opportunities for additive are enormous, but we have some important barriers to overcome. The processes, as they stand at the moment, are not necessarily as robust as they need to be. That's not a criticism of the guys selling machines. They come from selling prototyping machines. Production machines have to run consistently 24 hours a day, 7 days a week. They've got relatively poor productivity. Some of the best, Lars will be talking later on about electron beam melting. It's a good process. It's the fastest we have in terms of powder bed. But everyone would like it to be faster. We'd like it to be twice as fast, 10 times faster. Okay? If we double, there's a study done by a large aero engine company, and they worked out if we can halve the cost of making parts per kilo, we will increase the applications tenfold. If we decrease it again by a factor of 2, it's 100-fold increase in the applications that can be used for additive. So it's quite a dramatic shift if you can start to reduce the cost of parts. Typically, to produce 1 kilogram of components by powder bed costs around about 1,000 to 2,000 euros for a kilo. If you go to a casting company, they charge you maybe 10 euros a kilo. It's dramatically different. Another problem we have is part size, but that's starting to be addressed by the bigger machines. Surface finish is still an issue for all the processes. There are very few applications where you can take the part out of the machine, dust it off and stick it onto an engine. It's just simply not good enough. We're making really complex parts. They're difficult to inspect. We're making our lives very difficult by being clever with design. We did design for AM, and that's difficult. Our engineers are trained to design for conventional manufacturing. Additive is a completely new rule set. It is not true to say you can make anything by additive. I know we'd like to think that, but it's just not true. There are limits to what we can do with additive, and we have to train the next generation of engineers. It's too late for us The next generation of engineers has to be able to design for additive. We have a real issue in terms of materials and properties, and we have a real problem in terms of skilled people. For that reason, the National Centre for Net Shape Additive Manufacturing was set up at the MTC with the absolute objective of overcoming the barriers to introduction. We actually have two processes, net shape and additive. Net shape is taking powder and forming it in molds. Things like hot acidic pressing, SIP, HIP. You may have heard of metal injection molding, or even press and sinter, used to make con rods for cars. It's complementary to additive. This can do really high volume. Additive is freeform. You don't need tooling, so it's great. But it still doesn't have the productivity. You can't, people talk about tens of thousands of parts a week. It is not possible at the moment with additive manufacturing. Those are sort of technologies available that we're looking at. I'll go into a full list later on. The whole idea is to have a showcase demonstration factory, taking raw material and part designs, controlling the process to produce production quality components. So people can see it working, and then they can adapt the process for their own use back at base. This is a very expensive exercise. As I think you've heard figures of 60 million being, I think that's an underestimation for what we've invested. Most people get really fixated about the process. They buy a machine. They'll buy a machine from Renishaw, from Arcam, from EOS, from Concept Laser, and they get too fixated on that. That's not the problem. That's the problem. That's only a part of the process chain. And unless you can get to a finished part, you don't have a process. And powder bed is even more interesting because you only use the powder in its virgin state the first time. Then you have to recycle it. And all the properties you get change. They change as you recycle the material. So we need to consider the whole process chain. Design is critical. As I said before, if we're using the same design as a forging or a casting, it's a waste of time. We need to lightweight. We need to reduce the part count, integrate parts together. We need to think about how can we improve the performance. It might be flow properties or something else. We need to think about customization. Can we make a product and charge slightly more for it because it targets a particular market segment? And that's an example, not necessarily the best example, of a design for additive, where the conventional part, if you take the conventional part, which is normally machined, it's a 33-hour build by additive, by powder bed laser melting, weighs 100 kilos, the optimized production, 15 hours and 30 kilos. Okay. The figures don't really matter. The most important thing is you have to think about the design. The less material, the quicker the process is in terms of powder bed additive. The thing that we're trying to do is advise industry about all these different software tools. There's all these different specialized tools for lightweighting additive manufactured parts. So I think it was mentioned this morning about an automated process for designing parts for additive. I think we're partly the way there, but you need to understand the process. One of the things I would say is for India, this is a really good fit. You're already very strong on ICT. You could become the centre of design for additive manufacturing in the world. But if you're going to do that, you need to have an understanding of the processes, not just by the software. So there will have to be some centre in India that can provide the information that allows your engineers to use these software tools correctly. Another issue is control of powder. Now, if you've got a wire-based system, you'd have to worry about powder. It's great. But if you've got a powder-based system, the powder is essential. There is no point in buying the powder off Alibaba or whatever website you find, because if it's not the right powder, you'll end up making a terrible mess of the parts. Okay? The powder has a direct effect on the efficiency of the process and the quality of the parts. So we look at the chemical composition, the interstitial contamination, the particle size and the shape, the packing density, and very importantly, the flow. Flow is essential in additive manufacturing machines. If the powder doesn't flow properly, you don't get a good part. Okay. And interestingly, we even test new powder, and we reject new powder. Not very often, but when we reject a batch of 30,000 pounds worth of powder, the supplier doesn't tend to give it us again. Okay. We have lots of additive manufacturing equipment. We have laser melting equipment. Last year, our primary focus has been on electron beam for the last 2.5 years. And we've had lots of machinery on our shop floor. And to give you an idea of the scale of the activity, last year we were processing 1.5 tons of titanium powder a week. I think we're probably one of the largest users of electron beam in the world at that time. I mean, Lars might want to comment one way or another. We know that GE are very busy in this area, but I suspect at one stage, it may have been just 1 week, we beat their record. Okay. And only by making a lot of components do you understand just how robust the technology is. We also have a lot of DED equipment, laser cladding from 200 watts to 20 kilowatts. We have all sorts of arc cladding processes like MIG, TIG, PTA, and cold metal transfer. They're just standard welding processes. We hope at some stage to add other processes. We like the electron beam process. It's quite expensive though, even for us at £4 million. Was that dollars? I can't remember. No one's mentioned hybrid in the way that I interpret it. We've been pioneering the idea of a machine that adds material and subtracts it. So it's an effective machine tool that can add material. And there's significant advantages there. People have asked about accuracy and surface finish. Imagine you can get a part off the machine with the same accuracy and surface finish as a standard machine component. And the applications are not just new part production, but there's already, as Ashok's mentioned, customized parts, repair, and surface coating. And this is the Reclaim 1 machine was the first world first machine to combine laser cladding machine inspection in a single unit. And that was developed on the UK government programme. We also have this machine here, which is a retrofit Micron machine, slightly bigger laser. The interesting thing is it's a dockable system. Your machine does not change significantly. You just select a cladding head. So you can machine, add material, machine, add material at will. Post-processing, this is one of the things we say is the dirty little secrets of additive. The parts need a lot of work afterwards. We need to remove the powder, need to stress reliefs, remove supports, heat treat, and finish. And at the moment, there's a lot of manual processes there. We have to automate those processes, otherwise it just won't work as a business. And finally, if you can't inspect the part, you can't use it. And these parts are complicated. I'd love to show you some case studies, but the way that we're funded, we don't show anything unless our customer has released data to the public domain. So I'm going to say nothing about this case study. If you want to know about it, the slides will be made available to you. You can look at it and find this on the internet. I can say that it's allegedly the largest additive manufactured part in the world. This is an example of another project we got involved in with Mazak to generate the world's first multi-head hybrid machine. It's actually producing an oil and gas components at the moment in that little image there. And that has 2 heads, a high-rate laser cladding head and a fine detail laser cladding head. These are sort of things that we get involved in. We only have success once the part flies or once the machine tool can be sold. We don't get anything if we don't finish the job. What's next for AM? Final slide. Well, productionization of the processes is critical. We need higher power systems, multiple lasers or electron beam. We need larger build envelopes. We need increased process automation. We are making strides, And you'll see that most of the laser-based powder bed machines are now offering multiple lasers. Otherwise, it becomes a process that's not sufficiently fast. Thank you for listening, and hopefully later on there might be time for questions.
Jyotish Kumar to please felicitate Professor David Ann.